crypto. I'm super happy to have Mark. Well, he's a friend, a colleague, and we share the same alumnus and one PhD supervisor. So he worked on MPCs and ZK a very long while back. So that's more than 20 years now? 23 years now?
70 years, I believe.
Okay. Okay. So there you are. So he, in addition to working in Panther, he has been working on applications of ZK. And he has a whole bunch of papers, as any normal cryptographer would have. So he's a proper one, okay? Not a, you know. Mark, welcome to Zugrama, and please go ahead.
So I'm probably an old school cryptographer, not a sort of modern DeFi crypto person. So we're going to talk about ZK-SNARKs, and I'll start by saying something about the objectives and the approach taken in this talk. So the goal is just to give you an insight into how we can construct a ZK-SNARK. And we're going to focus in particular on pairing-based SNARKs, and I'll define what pairing means later on. And the approach is to try and keep things as simple as possible. So rather than give you full, complete and precise definitions, I'm going to be a bit loose in how we define things, and perhaps not define things fully. So just give enough information that we can move through the course, through the talk, and not get too bogged down with detail. It is an inherently mathematical subject, so there is some maths content. We kind of talk through what the maths means as we go through the talk. I should probably add that as an English person, I say maths with an S. I know some people might find that a bit strange. They say math, no S. So if you find that a bit strange, I apologise, but that's how I've always said it. In terms of this scope, we're not going to focus on any particular real-world SNARK. We're going to instead outline a type of SNARK construction that brings out the essential components or building blocks. And I'm not going to say too much about the zero-knowledge aspect as well, not in terms of how you actually build that into the SNARK. Partly just to avoid overcomplicating things and to try and keep things as simple as we can. So just to refresh your mind of what a ZK-SNARK is, it stands for a zero-knowledge, succinct, non-interactive argument of knowledge. And it's a way a prover can prove to a verifier that a computation has been performed correctly or that a given statement is correct. So the proofs are succinct, meaning they're short, fixed-sized proofs, irrespective of the size of the computation being verified. They're non-interactive, so there's no interaction between the prover and the verifier. And then we have the zero-knowledge property. The proof itself reveals nothing about the prover's private inputs. The only thing that the verifier can learn from the proof is that the statement is correct, or that the computation has been performed correctly. Learns nothing else. Oops, skipped forward there, sorry. So we'll actually start by looking at something that isn't directly used in ZK-SNARKs, but is perhaps a slightly easier introduction to the topic. And that is modular exponentiation. This is a foundational operation in public key cryptography. And it's defined as g to the power s modulo p, i.e. g multiplied by itself s times. And if anybody isn't that familiar with modular arithmetic, you can think of it as being remainders. You take g to the power s, you divide it by p, and you take the remainder. And that is the value of y. So p here is a prime number. And this is used in protocols like DSA, Diffie-Hellman, I'm sure some of you have heard of. What makes this function interesting is that it has this security property that given y, g, and p, it is computationally infeasible to determine s, provided the prime p is sufficiently large. And the current recommended minimum size for the prime p is 2048 bits in length. And this is called the discrete logarithm problem. Anybody familiar with the discrete log problem? Nobody at all? One. So just to make one observation, although during this talk I refer to this as encrypting S, or Y being the encrypted value of S, probably strictly speaking, it's not an encryption, because when you talk about encryption, you normally have the ability to decrypt, and you can't really decrypt here. So the more accurate way to describe this would be to say that this hides the value of S. But I will use the term encrypting as we go through the talk. Now, in addition to this security property we saw on the last slide, what really enables the construction of protocols like DSA and Diffie-Hellman are the inherent homomorphic properties of that function. There is a definition at the top here of what we mean by homomorphic, but it's probably easier just to focus on what these actual properties are in this instance. Before doing that, though, I'll just stress that schemes like DSA and Diffie-Hellman, they're not what we talk about as being homomorphic schemes, not fully homomorphic or anything like that. They do possess some homomorphic properties. This is what we're talking about here. But they're not homomorphic schemes, that signature schemes and key agreement schemes, things like that. So the two properties are that given the encrypted value of A and the encrypted value of B, we can work out the encrypted value of A plus B simply by multiplying together the encrypted value of A and the encrypted value of B. And the second property is that given the encrypted value of A, we can work out the encrypted value of A times B simply by taking the encrypted value of A, raising that to the power of B. So homomorphic properties such as these, say this is what we rely upon to build schemes like DSA, Diffie-Hellman. You don't find properties like this in symmetric ciphers. In fact, when you design symmetric cipher, you make good efforts to make sure you destroy any kind of mathematical structure, because that can normally be a weakness. So that's one difference between the public key schemes and symmetric key schemes. And perhaps just to remind you from what Nish told you yesterday, difference between public key schemes and symmetric key schemes. With a symmetric cipher, the encryption key is essentially the same as the decryption key. So you know one key, you know the other key. And these schemes tend to be very fast, efficient, and those are the type of scheme that we use for encrypting data. With public key schemes, two keys are related mathematically, but it's computationally infeasible to determine one key from the other key. So you know the encryption key, for example, you cannot derive or work out the corresponding private key. That's why you can, in effect, make one key public. So the encryption key is public. Anybody can encrypt, but only the party that knows the corresponding private key can decrypt. But coming back to the focus of this talk, this operation, modular exponentiation and schemes like DSA, Diffie-Hellman, they are defined to work in what mathematicians call a group. We won't define what a group is. We don't really need to know. Just that in our case, it is a set of integers 1 up to p minus 1 with multiplication modulo p. So one interesting question is, are there other groups that have the same, got echoey, is that me? Or, yeah. Oh, okay. Are there other groups that give you the same security property of this discrete log property? And the answer is that yes, there is. It's called elliptic curves. And again, this is something that Nish touched on yesterday, and he gave you a diagram. No diagrams here, but just a straight definition. An elliptic curve is just a set of solutions, meaning values x and y, that satisfy an equation of this form here. Y squared is equal to x cubed plus ax plus b. Where the coefficients a and b and the solution, x and y, which we often call a point, belong to another structure loved by mathematicians called a field. Again, you won't define what a field is, we just say, well, we won't formally define what a field is, we just give an example here, which is a set of integers from 0 to p minus 1 together with multiplication and addition modulo p. And what makes elliptic curves interesting, apart from the fact that they have this security property, is that you can add points using this special type of addition. So you add 2 points to get a third point on the curve. And this was Anish's diagram yesterday. We had a line between 2 points intersected the curve and we drop down. That's the kind of addition we're talking about. So if we take this set of points or solutions together with this addition rule, then that defines a group. So schemes like Diffie-Hellman and DSA that work in a group, they also work in this elliptic curve group. That's why you get elliptic curve versions of schemes like of Diffie-Hellman and DSA. One difference, though, with the elliptic curve group is that it is an additive group, not multiplicative group, which means we define the discrete log problem in a slightly different way. We now say that given 2 points P and Q, it is computationally infeasible to determine the value S, or the number S, such that Q is equal to SP. As you mentioned on the last slide, the coefficients A, B, and solutions, or points x, y, belong to this field. And this field is called the base field of the curve. And there is a second field associated with the same curve, which is called the scalar field. And it's to the scalar field that this integer s belongs. So what this all means is that when we talk about Snark works over an elliptic curve. But the circuit, or the statement that we're going to prove, that works in the scalar field of the curve, not the base field. And the implication of this is that if your statement or your circuit includes a public key operation, a Diffie-Hellman operation, for example, then the base field of the Diffie-Hellman operation should align with the scalar field of the Snark. When I say should align with, some reason has disappeared. Back, okay. It should align with, that's to do with efficiency. If the two fields don't align, then you can still, or the Snark can still do the verification, but the circuit just blows up and gets hugely, much bigger. So if you have any choice over your parameters, you'd make sure the two fields do align. But there are some cases, such as bridging, for example, where you may not have any choice over your curve parameters, and you may have to handle this non-native field arithmetic problem. And to give you some examples of curves, BN254 is a curve commonly used by Snarks. And Baby Jub Jub is a curve that's designed to align with the scalar field of BN254. So our Snark will be using BN254, and our DSA, for example, will be using Baby Jub Jub. So those are a lot of things to throw at you in one go, but yes, this gives some idea of why I have these different curves and how they kind of fit together. Any questions as we go along, by the way, just shout out. And if you want to pause on a slide, just, yes. With the scalar field of BN254. Right. Yeah. So I forget which ones are of recursion, but I think possibly yes. Yeah. I have to double check though. Coming back to the homomorphic operations, and just to define these again in the elliptic curve setting, we have that given the encryption of values B and C, we can compute the encrypted value of B plus C just by adding together the 2 points, which are the encryption of B and the encryption of C. And the second property is that given the encrypted value of B, we can compute the encrypted value of B times C by taking, it's gone again, back again. I'm not touching the wires. I'm not sure whether just by moving somehow is causing it to fade out. So yes, given the encrypted value of B, which is the point, compute that by C, get the encrypted value of B times C. But what we cannot do, unfortunately, is to take the encrypted value of B and the encrypted value of C and work out the encrypted value of B times C. Nice if we could, but we can't do that. But one of the advantages of using elliptic curves over the more sort of conventional approach we started with is that we have the existence of something called pairings. So in this next slide here, we define what a pairing is. I'm not going to go through that. It's there if you're into the maths and you want to understand a pairing. I'm going to focus more on what a pairing lets us do. So if we're given something like A times B is equal to C times D, we want to put that into encrypted form and verify that statement is correct, we can do that using a pairing. Take the encrypted form on both sides, compute the pairing of the left-hand side, the pairing of the right-hand side, make sure the two things match, and that verifies that the encryption is correct. And some examples of pairing friendly curves are BN254, BLS12381. And when we say pairing friendly, what we mean is efficient. So the efficiency of a pairing is determined by something called the embedding degree. Again, you won't define what that is. But if that is too large, the pairing's inefficient. If it's too small, then you can attack the curve. So it's about making sure this thing called the embedding degree is large enough to be secure and small enough to be efficient. There are some additional requirements for our curve for SNARKs to do with efficiency. FFT friendly, for example. And so the choice of curves isn't that huge. One thing you can do using these homomorphic properties of elliptic curves is to evaluate a polynomial p of x, it's just defined here by the coefficients a0 up to an. We can evaluate that in encrypted form at a secret unknown value s using only the encrypted forms of s. And that's a bit of a statement to come out with, I'll let you read through. So the encrypted forms of s are these points Nope. Nope. It's not that, just some kind of weird vibration.
Maybe if you could just tap the screen.
No. So where were we? Oh, maybe I'll stand further away from the screen this time. So the encrypted forms of S are these points P0 to Pn. And so our evaluation of this polynomial P of x at this value S in encrypted form is just a combination of these points P0 to Pn and the coefficients A0 to An that define a polynomial P of x. And this short, fixed size representation of PS achieved, the encrypted form of P at S, is called the commitment to P of x. And it's called a commitment because once you've committed to it, you can't then change that polynomial. Trying to find a second polynomial that encrypts to the same value at S is difficult because you don't know S. And given the numbers are very large, its chance of it happening is so small, it's not going to happen. It's also worth just noting that the encrypted value here keeps the polynomial coefficients secret. So we can expand on this idea of commitments to something called KZG commitments. what we can do here is that given a commitment to a polynomial p of x, we can then prove that the same polynomial evaluated at value v is equal to y for some known values v and y. And we can do this without revealing the polynomial p of x, which is quite an interesting thing to be able to do. This works because if p evaluated at v is equal to y, then mathematically it's true that p of x minus y is divisible by x minus v. If you're not familiar with the maths, just believe me on this one. You can always look it up afterwards as to why. So this means that p of x minus y is equal to x minus v times some polynomial q of x. And that's true for any value of x. So it's also certainly true for our value s that we've been using in the last few slides. So we have this equation here, which we can put into encrypted form. This is going to be the encrypted form of q of s and the encrypted form of s minus v. It's a product, therefore we can use pairings. So we can verify the correctness of this equation here in encrypted form by taking the pairing of the left-hand side, the pairing of the right-hand side, and making sure the two things are equal. I won't go through all the values used in this pairing, but here is our commitment value down here, for example. So, having come this far, our task now is to express the computation in such a way that we can verify it using the homomorphic properties of elliptic curves and pairings. And we can do this using arithmetic circuits and constraints. So an arithmetic circuit is a way of representing a computation as a sequence of additions or multiplications over a finite field. Because we're working over a finite field, it means that some computations will be more efficient or friendly than others. So to give an example of a hash function, Poseidon is a modern hash function designed to be efficient in SNARKs. It works well over a finite field. Something like SHA-256 is a very widely used hash function. It's a NIST standard hash function. And that's not so efficient in a SNARK because it doesn't adapt so well to this representation over a finite field. We also have a constraint system, and this ensures the computation's correctness by capturing the relationship between the inputs and output of each stage in the sequence of operations. So there typically be two inputs, a left and a right, and an output. And each constraint, i.e. each step in this sequence of operations, represents an addition or multiplication by a constant. Not the case that you have to be restricted to two inputs. Sometimes you can have more than that, but we'll stick with two inputs just to keep things simple. And examples of constraint systems include R1CS, as used in something like Groth16, or we have a Planck-type arithmetization. So again, who's familiar with R1CS or Planck or Groth16? Anybody? Oh, it's a few. That's good. So we're going to follow a Planck-like constraint construction. It's not a full Planck-type constraint. We've kind of simplified it a bit. That's the kind of constraint we use with Planck. So these polynomials, I call them the Q polynomials just to keep things simple. The QM, the QL, the QR, and the QO. Those specify the circuit. Whereas the polynomials A of x, B of x, and C of x, that represents the prover's assigned values. What we call the witness. So A of x is the left input, B of x is the right input, and C of x is the output. And then each constraint in our sequence of operations is represented by a specific value of x. So this means we take this polynomial, we take a particular value of x, and we evaluate all these polynomials, the b's and the a's and the c's, at that value of x, and that will define a particular constraint in our sequence of constraints. So to give one example, in this case an addition constraint. So the operation we're looking at here is that x plus y is equal to z. So x plus y, x and y are the two inputs, z is the output, which we write as x plus y equal minus x plus y minus z is equal to 0. So for this addition constraint, we want that qm, m is multiplication, qm will evaluate to 0, ql and qr will both evaluate to 1, and that qo will evaluate to minus 1. And we put those values for these q polynomials into our constraint polynomial. What we get is that a of x plus b of x minus c of x is equal to 0, which is what we had up here. Just to give you one further example, we'll consider an addition gate for the sum 5 plus 11 is equal to 16. And this constraint is defined by the value x equals 3. It's an addition gate, so qm at 3 will be 0, ql and qr at 3 will be 1, and qo at 3 will be minus 1. So polynomial a of x evaluated at 3 will be 5, which is the left input. The polynomial b of x evaluated at 3 will be 11, which is the right input. And the polynomial c of x evaluated at 3 will be the output. We put these values into our constraint polynomial, and what we get is 5 plus 11 minus 16 is equal to 0, which is what we want. So let's give this polynomial that defines our constraints a name. We'll call it m of x. So what we have done is we've defined m of x, or constructed m of x, in such a way that it will evaluate to 0 at a specific set of inputs w1 to wn, where each input w1 to wn defines a constraint in our sequence of constraints. So that is, each wi corresponds to one constraint in our circuit. So what this means is that this polynomial m of x is divisible by x minus wi for each of our wi. So if we define a polynomial z of x to be the product of all these x minus wi polynomials, then what we're really saying is that z of x must divide m of x. Let's people think about that for a moment, because I'm doing some looks. This is what we're going to use to build our snark. Before we look at the actual snark construction, though, just make one observation, which is that given some challenge value v, if we are also given the evaluations of a of x, b of x, and c of x at that value v, we can then construct the value of m evaluated at v. Just by plugging the values into this equation we have here. Now the q polynomials, the ql, the qr, and so on, they're public. So we know those polynomials, we know the value of v, you can compute the evaluation of those polynomials at v. So if we know the evaluations of these q polynomials at v, and we know a of v, b of v, and c of v, we can then compute the value of m of v. But in order to know that our evaluation of m of v is correct, we need to know that these values here are also correct. And provided we can do that, we then know that our evaluation of m at v is correct. And so we can do this using our KZG commitments. You commit to your polynomials a of x, b of x, and c of x. You then see your challenge value. As we saw a few slides back, you then prove that your values a of v, b of v, and c of v are correct. People mostly happy so far. Okay. So now we put it all together to create the snark. And in essence, the snark is the proof that, first of all, the polynomial m of x is properly constructed according to the q polynomials. And secondly, that m of x is equal to r of x times z of x. That is, that m of x is divisible by z of x. What we're going to rely on in this proof is that the prover commits to a set of polynomials prior to seeing the challenge value v, that the relationship between the polynomials then holds at this challenge value v. So here is the proof generation process. The first step is to compute the polynomial r of x. So the prover will take their assigned values. These assigned values determine the coefficients of the polynomials a of x, b of x, and c of x. Once you know those polynomials, you can then compute the polynomial m of x. You divide m of x by z of x, and you get r of x. The prover then commits to the polynomials a of x, b of x, c of x, and r of x. Once those are committed to, you get the challenge value v, and you provide the evaluations of a of x, b of x, c of x, and r of x at that value v. For the verification, you first verify that the values, or the provided values of a of e, and b of e, and c of e are correct. That's a KZG commitment verification. That's using pairings. We then verify that the provided value of r at v is correct. That's again using pairings. We can then construct m of v, because we know the correct values of a of e, b of e, and c of e. We compute z evaluated at v, because we know z, we now know v, just compute z of v. And finally, we verify that m at v is equal to r of v times z of v, i.e. that m of v is divisible by z of v. And that is the end of this part of the talk on the Snark. So I'll have some other things to go on to now. That's the like the core technical part of the talk covered. Any questions so far, by the way? We can wait till the end if you prefer. No? Okay. So now look at one example of where Snarks are used in practice. So this is a project I've been working on for a while. It's a project that makes extensive use of ZK-SNARKs. And the project is a modular, composable suite for compliant digital finance. And it can be applied in many different scenarios. We talk about transaction compliance, compliant wallets, accountable or self-sovereign IDs. So all these different use cases are benefiting from the use of ZK proofs. Doesn't necessarily have to be SNARKs, it could be SNARKs, but it's ZK proofs. And there are other use cases we could look at beyond here as well. In terms of the project, it gives you regulatory compliance across multiple different DeFi protocols and applications. So we're here looking at enabling per transaction compliance that meets regulatory objectives for anti-money laundering, for example, while also protecting user privacy. So we're trying to balance compliance and privacy. Importantly, it does maintain the autonomy of the DeFi protocols and applications themselves. So if it's present, you can have compliance. If it's not there, the protocol can carry on as before. It's just not proven to be compliant. So the protocol itself maintains its autonomy. In terms of how you can use this, it can interface with the protocol at a wallet level, and it can handle all compliance and give you your compliance assurance, and you can direct that accordingly. So in the case of a privacy providing protocol, it's directed towards the protocol itself, and the protocol can itself guarantee or provide assurances of compliance. And it can also integrate with things like smart contracts for real-world assets, for example. Also had the use case of self-sovereign IDs or data. So it could be the case that you want to be able to authenticate by at the same time at the same time protecting your true identity. But if you do misbehave, shall we say, then you can be held accountable and your identity is revealed. So trying to balance the needs here. We always have a case where you may have encrypted data stored somewhere, and you, the owner of the data, maintain your privacy. There may be some kind of business requirement or legal requirement that you have to reveal the true owner of that data at some point. Also enables data owners to prove they own data while at the same time maintaining their confidentiality, which can be quite nice. In the case of AI agents, we get things like gaining trust in AI agents, improved efficiency, scalability, interoperability. Agents are using a common compliance architecture to help with interoperability. So we're talking about building applications faster and cheaper by using a common off-the-shelf compliance architecture. There's a quick look at of the scheme itself, and just to end, it is perhaps as you'd expect, all mathematically worked out and nice and proven to work. And that is the end of the talk. So, well, thank you. So, any questions? Mm-hmm.
Just start at the beginning again. The second, can we go back 4 slides, please? Yes. So can you explain this one with an example and the next slide, with this is the agent with an example, and how you'll be using ZKs for that?
Any particular part of?
I would go with the Web3, the Web3 user accountability and self-sovereign, because we've discussed privacy about this yesterday and I was not very convinced of how privacy happens in the current Web3 architecture. So how do you think would ZK support that?
I guess a very simple example here would be, say, a social media site. We want to have an account. We want to protect your true identity. So you can still prove that you are. Just best way of describing that. You can use an anonymous shielded identity to access the account. Persona, essentially, yes. And you can prove that if need be, and you do misbehave, that you can be held accountable. So the proof is more in making sure that you can be held accountable part, knowing that can happen. Mm-hmm. Mm-hmm.
Yeah, I thought you were going to answer that question a little differently. Do you mean that the persona can be held accountable, or that the root identity can be held accountable? Because, okay, but balancing privacy and accountability is like one of the hardest problems to solve. And if you have any ideas there, I'd really like to hear them, because it's like, it's a bit like putting a backdoor into like cryptography that would allow, it's like, what's the logic gating that allows you to say, reveal this identity if they engage in this misbehavior and don't reveal it under other circumstances? It's like, who has the ability to upgrade something equivalent to a smart contract means that it's always subject to like abuses by people that have the ability to do that. What are your thoughts on that?
I think that's an interesting conversation.
Okay.
I think obviously the topic of this talk was the ZK-SNARK bit, so I don't want to go too much into this.
Sorry, I just
pick it up,
that was a juicy bit. I'm going to ask you about that later. Okay.
Anybody wants to ask about the compliance project, find me afterwards and I'm happy to talk to you for ages on that.
I was going to go into a similar line, which is about where does the border for accountability and privacy lie, because this was a discussion yesterday as well.
Yeah.
And to extend from that. And the next slide, which is about agents. Again, with agents, when you think of who, like, say, for example, there are multiple companies who are trying to interact on the chain with the help of agents. Where does the responsibility lie? Where does the privacy lie? And also, how is the information held in a fashion? Like, what element of the interaction would be kept on the chain, which is proven with ZK, and what elements? So if you could just cite this.
Again, it's probably a good discussion to have, maybe.
Okay, this
Yeah.
also.
I
Okay.
think just because we talk about the snark side more than this is more an example.